Okay, so welcome everyone to the ICT String seminar. Today, we're very happy to have David Pollan from Yale telling us about charting the landscape of 3D CFTs. So please, David.
All right, thank you very much. It's a great pleasure to be giving this seminar. So I thought I would try to tell you about some of the progress that that we've made in pursuing the conformal Bootstrap program over the last couple of years. And in particular, most of my talk today will be focused on what we can learn about three-dimensional conformal field theories using conformal Bootstrap techniques. So the idea behind the Bootstrap is very straightforward. The idea is to use basic consistency conditions and symmetries to try to map out and solve the space of conformal field theories. Ideally, you could come up with a kind of classification of conformal field theories. The hope behind the Bootstrap is that you can use this additional symmetry in conformal field theories, which in d-dimensional theories is SOD(2) or SOD+1(1), depending on whether you're in Lorenzian or Euclidean signature. In addition, you can try to use constraints like crossing symmetry, which tell you that if you take correlation functions and expand them using the operator product expansion in different channels, then those expansions had better be equal to each other. And then finally, we can use constraints like unitarity in quantum theories, or its Euclidean incarnation, which is called reflection positivity. So the hope is you can put these constraints together, and that maybe they're so constraining that you can uniquely identify solutions compatible with these constraints, or at least constrain the space of observables in some interesting way. And of course, there are many motivations for studying conformal field theories, but one of the most down-to-earth motivations is that they're relevant for the physics of critical points, such as you can find in a temperature pressure diagram in any fluid. So of course that in turn means that there's lots of experimental data about critical exponents, power law behaviors associated with critical points in a variety of different materials. And these critical exponents can be directly related to observables in a conformal field theory describing the critical point, in particular, the scaling dimensions of operators. So one of the main constraints we use in the conformal Bootstrap is crossing symmetry. So let me just explain the simplest version of crossing symmetry. So the idea is that you can look at a 4-point correlation function, sigma of x1, sigma of x2, sigma of x3, sigma of x4. In a conformal field theory, there's an operator product expansion, which can be convergent. And so if you apply the OPE between sigma of x1 and sigma of x2, and then also sigma of x3 and sigma of x4, you get one expansion of the 4-point function in terms of all the operators that are exchanged in the OPE, along with their OPE coefficients, lambda, sigma, sigma, O. And then if you require that expansion is equal to the expansion that you get when you take the 1, 4 and 2, 3 OPE, then you get a kind of constraint on the theory. So in practice, these expansions take the form of a sum over OPE coefficients squared times a kind of special function called a conformal block, which depends on the scaling dimension and spin quantum numbers of the exchanged operator. And it's a function of the 4 coordinates entering the 4-point function, but they combine together into 2 conformal cross ratios. So z and z bar are particular combinations of the 4 coordinates that are invariant under any conformal transformation. Okay, so the main thing to emphasize here is that crossing symmetry gives you a kind of sum rule. A sum over conformal blocks in one channel equals a sum over conformal blocks in another channel, or you can say the sum over the difference has to vanish. And sitting in front of those conformal blocks are the squares of OPE coefficients, which in any unitary or reflection positive theory, these are positive coefficients. Okay, so the main unknowns in this equation are the scaling dimensions of the operators and the 3-point coefficients. So, okay, there are different ways you can tackle this equation. You can try to study it analytically in different limits, or try to take integrals of this equation and see what you can get. Or you can study it numerically. So I'm going to start off by telling you about some numerical progress in studying the crossing equation. And the idea behind the numerical approach is that this sum rule basically tells you that a sum over functions with positive coefficients has to equal 0. Let's think of these functions as being like vectors which live in some vector space. So you're saying, I want to sum up a bunch of vectors with positive coefficients to get the 0 vector. And in some cases you can do that, and in some cases you can't do it. So you can sum up a bunch of vectors to get the 0 vector if they're all pointing in random directions, and you can cancel them against each other in some way, like the left plot. But you can't do it if you're in a situation like the right plot, where all the vectors point to one side of some kind of plane. You might call it a separating plane, alpha. And so the basic numerical approach is you make some assumption about the spectrum, and then you ask, okay, is it possible to find a separating plane that puts all the vectors to one side of it? And if you can find such a plane, then it's not possible to solve the crossing equation with positive coefficients. And in practice, the way we search for the separating plane is by applying some functionals to the crossing equation. Namely, we take linear combinations of derivatives with respect to the cross ratios evaluated at the most symmetric point, 1/2, 1/2. And in order to make it into a sort of finite problem that you can put on a computer, in practice, we take derivatives up to some order defined by a number lambda.
Maybe one question.
Yeah.
So when one does this numerical bootstrap, why is it that this set of functionals is chosen? I mean, is it better in some sense than other functionals that one may write down from numerical point of view, or from the view of the kind of information that you want?
So yeah, that's a really good question. So this is a set of so this is a question about what basis you should use for these functionals. And here we've picked some particular basis given by derivatives at the point 1/2, 1/2. So there are various nice things about this particular basis. 1/2, 1/2 is the most crossing symmetric point, so it treats the S channel and the T channel in a completely symmetric way. This is, by the way, is the configuration where all 4 points in the 4-point function are put in a square. So it's sort of easy to see that it's symmetric under in the different channels. Yeah, there are lots of other bases you could choose. You could try derivatives around different points. You can try just evaluating the 4-point function at different points. Or you could try, taking various integrals of the 4-point function. So these are all directions people have explored. This 1/2, 1/2 derivative basis, seems to work very well in practice. It's sort of easy to implement, and it works well with one of the other techniques that we've developed for the conformal bootstrap called semi-definite programming approach. But there's a lot of interest right now in other kinds of functionals, sort of motivated by analytical bootstrap approaches. Functionals which act nicely on the spectrum of operators in generalized free theories, and the hope is that one of these other functionals might give you a much more convergent numerical bootstrap algorithm. But so far it hasn't sort of quite panned out in practice yet.
But if one sticks to expanding around a point, let's say, then half, is it somehow inherently better than any other choice from this point of view, or just because it's a crossing symmetric point?
It's because it's a crossing symmetric point. So the second you go to a different point, then what it means is that one of the channels is going to have worse convergence.
No, but isn't there a point even more crossing symmetric than this? which is you move off on the complex plane, so that it's STU all crossing symmetric.
STU all crossing symmetric.
Meaning, let's consider a sphere with points being on the regular tetrahedron. That is inside the sphere.
Mm-hmm.
That it seems like the most crossing symmetric configuration, right? Rather than choosing a planar configuration, which is what this is, right? A planar configuration.
Yes, that's right.
But now, if you take a two sphere and inscribe a regular tetrahedron in it, and pick those points, that's some I forget now. There's some cube root of unity or something like that comes up. You can cross ratios come out to something like that. That seems to be crossing symmetric from all three channels. Just a thought, and I don't have anything to say about it, but this seems like even more crossing symmetric. If that is the case, then this seems like even more crossing symmetric. So is it possible that this could turn out to be better, or are there any expectation? A priori expectation that this choice is better actually, the half choice.
Yeah, I guess the question is what the convergence, how quickly the OPE converges in the different channels. So I'd have to think about the point that you were describing.
Thank you.
But yeah, these are interesting ideas. Okay, so let me go on. So this is the particular choice that we've sort of converged on for numerical Bootstrap applications, though it's very interesting to think about other possible functional bases. So now, so in practice, you can search for these functionals which define a separating plane and would imply some kind of contradiction by solving a kind of convex optimization problem. And so in the modern numerical Bootstrap, we phrase these in terms of optimization problems called semi-definite programs, which are basically problems where you optimize some quantity subject to constraints which involve positive semi-definite matrices. And so there's an efficient software tool for solving these semi-definite programs called SDPB, which was written by one of my collaborators, David Simmons-Duffin, and is freely available. Sort of in addition to this basic semi-definite program solver, there have been a variety of other kinds of advances in the numerical Bootstrap in recent years. So let me just briefly describe a few of them. So one of them is that this semi-definite program solver, SDPB, has been sort of recently enhanced to be more efficient, more parallelizable on computing clusters, and is much faster than it used to be. Another advance is that we've developed various algorithms for sort of searching through the CFT parameter space, in particular the space of allowed scaling dimensions and the space of allowed OPE coefficients. So we've developed something called a cutting surface algorithm for sort of efficiently finding allowed values of the OPE coefficients in large parameter spaces. And we also developed something called a tip-top algorithm for trying to maximize some scaling dimension over some multi-dimensional parameter space or island in the space of CFT dimensions. And finally, we also developed a new software tool for doing sort of efficient computations of conformal blocks in 3 dimensions when the external operators have some spin. So previously, there were a few studies involving external spinning operators like fermions and currents in the stress tensor, but they were all very hard to do. And in particular, computing the conformal blocks took a lot of work, and it wasn't sort of easy to generalize those techniques to other situations. So now we have this fairly efficient software tool which can compute arbitrary conformal blocks involving spinning operators. Okay, so I'll show you some applications of these software tools a little bit later. Let me just mention for anyone who's sort of interested in getting involved in the conformal Bootstrap, the Bootstrap collaboration has a GitLab website which is collecting a bunch of these different software tools that people have developed, and it's freely available. Okay, so what can we do with this numerical approach? Okay, so I'll show you, flash a few older results first, and then I'll show you some newer results. So, one of the sort of exciting earlier results from the numerical bootstrap in 3 dimensions was this bound, where we place a bound on the scaling dimension of the operator, the leading operator, scalar operator epsilon, appearing in the OPE between 2 scalar operators sigma. And so if you assume that the scaling dimension of epsilon, or the gap in the spectrum, is too high, then you can prove that there exists this kind of separating plane, which shows you that crossing symmetry can never be satisfied in a way compatible with unitarity. So that's this disallowed region. Whereas if you're below the curve in the allowed region, then you're not able to find such a separating plane. And so there may or may not be CFTs living in this allowed space. This is coming just from looking at a single 4-point function, sigma, 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 sigma. So the interesting thing about this plot is that, it starts at the origin at the free theory value of the scaling dimension of a free scalar is 1/2, and the epsilon operator would be like sigma squared, which has a scaling dimension of 1. But then it goes up and has some kind of funny kink in it, and that kink happens to coincide with the scaling dimensions of an interesting 3-dimensional conformal field theory, which is the 3-dimensional Ising model. So we sort of, plug in this machinery, we can start computing bounds like this. And then, it raises a lot of questions, like why is the 3D Ising model sort of special and live in the kink? And then also, can you sort of push this further and come up with some, we have this rigorous exclusion plot, but can you actually get some rigorous determinations of the scaling dimensions in the 3D Ising model using this observation? So it turns out that you can do the latter by going to a system of mixed correlators. So you consider 4-point functions involving both sigma and epsilon. And so you consider the 3 4-point functions, sigma, 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 epsilon, epsilon, and epsilon, 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 epsilon. Here we're assuming sigma, there's a Z2 symmetry where sigma is Z2 odd and epsilon is Z2 even. And then further, we can assume that sigma and epsilon are the only relevant operators in the theory. This is an assumption that is sort of experimentally motivated for systems in the 3-dimensional Ising universality class, like liquid gas transitions, liquid vapor transitions, because like the temperature pressure diagram is a 2-dimensional space, and you have to tune 2 parameters to get to the critical point, and that tells you that there are 2 relevant operators in the CFT. So if you make that assumption that sigma and epsilon are the only operators with scaling dimension less than 3, then it actually lets you isolate an allowed region around the 3-dimensional Ising model solution, which is separated from some sort of bulk region to the right, where maybe other CFTs could live. Okay, so now you can try to push. I'm
sorry, can I ask a question?
Yeah, please do.
So when we do this numerical bootstrap and we get these graphs and so on, is it all, this delta epsilon, the y-axis here, is that always the first exchanged operator in these OPs, in the sigma OP, sigma epsilon OP, and so on?
Yes.
Okay, so you can't find like a similar graph for the next operator after epsilon in the OPs.
You could, so you could assume some particular value of delta epsilon, and then you could make a similar plot for a bound on delta epsilon prime, for example.
Okay.
Or you could add epsilon prime as another axis and make a 3-dimensional plot. Yeah, you can do all those kinds of games with higher dimensional operators, but usually you have to then sort of assume something about the lower dimensional operators first.
Okay, I see. And what about spin? In general, this first exchanged operator should be a spinning operator, right? No, that's not really true. Sorry. But I was just thinking, like, you can probably also get some graph where you have the spin and
Yep.
okay.
Yes, absolutely. So But so you can distinguish between different spins. So here, this is a graph specifically for the leading scalar spin 0 operator. But you can also produce bounds on operators with spin. So you can, bound the leading spin 2 operator in the sigma sigma OPE, and you bound
Correct.
this leading
Yeah,
spin
I
4
see.
operator, and so on. Yeah.
Thanks.
Yep. Yeah. So there are a lot of operators, and there are a lot of games like that you can play. So it takes, it's a bit of an art form to try to figure out what are the most interesting plots to make. Okay, so yeah, so here we understood how to get this island, and now you can ask, what does it take to shrink it further? So one thing that helps to shrink it further is to actually input some information about the OPE coefficients involving sigma and epsilon. So in particular, one thing that's very helpful to do is to say that, okay, there's some OPE coefficients involving sigma and epsilon. They have some ratio, lambda epsilon 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 over lambda sigma sigma epsilon. And in a theory where there's only a single isolated sigma operator and a single isolated epsilon operator, this ratio will have a unique value. And you can then try to distinguish it from theories where you might have multiple degenerate operators at the same value of delta sigma and delta epsilon, where you get contributions to the OPE, which multiple degenerate contributions to the OPE, but they have different values of the OPE coefficients. So so one thing that's helpful to do is to basically input this information that there's a unique isolated sigma and epsilon operator by inputting some value for this ratio of OPE coefficients, and then sort of scanning over all possible values. So what this effectively does is it lets this functional depend on the ratio of OPE coefficients, and this gives it sort of more freedom to come up with a smaller allowed region. So that requires mapping out a 3-dimensional parameter space, but it lets you shrink this allowed region further. And then finally, the other thing we can do to shrink the allowed region further is to go to higher derivative order, increase the search space for this functional, increase lambda, this lambda parameter. And so putting that all together, we were able to get a very, very small, essentially rigorously, we can essentially rigorously exclude everything around this small island, given the assumptions that we made, which would be true of the 3-dimensional Ising model, and then we can get fairly precise determinations of the leading scaling dimensions, as well as the OPE coefficients. Here, yeah, you can sort of see that the Bootstrap determination is roughly 2 orders of magnitude smaller than the best Monte Carlo determination. So at least for this particular 3-dimensional conformal field theory, the Bootstrap techniques seem to be more efficient than conventional Monte Carlo techniques.
Sorry, just a quick question.
Yeah.
So what kind of machine did you need to produce these plots? I mean, did you need like large clusters, or is it something that...
So, yeah. Right, good, yeah, good question. So you can, you can basically produce, you can produce this kind of bound, which is fairly low derivative order. You can do that on a laptop. It's not too bad. But to really push to high derivative order, here we push to like 1,000 components, 1,000 different derivatives that we were scanning over, then that required a cluster. So this, yeah, this computation, this was actually using, older, the less efficient software tools than we have now, but it took something like 2 weeks running on a computing cluster.
I see, okay, thanks.
Yeah. Okay, so there are other interesting 3D CFTs. So another interesting class of 3D CFTs are the ON vector models, where you have, if you can think of the Ising model Wilson-Fisher fixed point description as a scalar field, which has a quartic interaction. You can generalize that to n scalar fields, which have quartic interactions, which preserve an ON global symmetry, which rotates between them. And different values of n are interesting. So the O2 model, or sometimes it's called the XY model, is experimentally very interesting because it describes the superfluid transition in substances like helium-4. And there's fairly precise experimental data, which was taken aboard a space shuttle mission in the 90s. So they put a sample of helium-4 up into space and measured the heat capacity of the helium-4 as you cross the superfluid transition. So these data points on the right are showing the heat capacity as a function of temperature as you cross over the critical temperature. And so from this kind of data, you can extract power law behaviors, which give you critical exponents, and then you can potentially compare those to constraints from the Bootstrap. The O3 model is also interesting. It's sort of the conventional, sometimes called the Heisenberg model. It's sort of the conventional model of ferromagnetism. So sort of you expect it to describe isotropic ferromagnets, where the underlying spins of the ferromagnets are free to rotate in 3 dimensions. And then a large N is also interesting because you can solve these theories analytically in a 1/n expansion. Also, there are interesting connections to ADS CFT and Vasiliev theory on large N. So, okay, so you can apply these numerical bootstrap techniques to the ON models. So if you just compute the basic bounds, looking at 4-point functions of phi I, where phi I is a vector under the an ON global symmetry, you can take that 4-point function, expand it in different ON tensor structures, read off a crossing relation sitting in front of each tensor structure, and then plug in that system of crossing relations to the numerical bootstrap. And then you can place bounds on scaling dimensions of different operators. I mean, again, you have a choice. You can bound spin 0 operators or operators of spin, and you can also bound operators in different symmetry representations of ON. So this plot is showing a bound on the leading ON singlet operator, which is also a scalar, which we called S. And these bounds sort of show a similar structure to what we saw in the Ising model case, where for different values of n, you get some bound with a kink in it. If you go to large N, you can compare the locations of those kinks to the predictions in the 1/n expansion, and you see that there's very good agreement. For example, in the case of O20, there's this black plus. These black pluses are the large N predictions for different values of n, so you can see that there's a black plus in the O20 kink and also the O10 kink. And then the large N expansion sort of breaks down when you go to small n, but there's various experimental or lattice simulation data that you can compare with, and you also see good agreement for example, O2, O3, and O4. So something about the Bootstrap definitely knows about this sequence of theories in some very interesting way. Okay, if you then go further and turn this, you can turn these kinks into islands again by considering a system of mixed correlators. So here we looked at a system of 4-point functions containing the leading ON vector phi I and the leading singlet S. And in this larger system, you can then input that phi and S are the only relevant operators in their respective symmetry representations. And under that sort of mild assumption, you can get some closed regions, which are allowed by the Bootstrap. Each of these is also disconnected from some other sort of bulk region, which is off the plot to the right. Okay, so these regions that we obtained in this way are sort of a bit bigger than what we got for the Ising model, but they still allow us to isolate the solutions. So here's a zoom in on the region we got for the O2 model. So these islands show the bootstrap allowed regions for different values of lambda as we increase the derivative order. And those can be compared with the Monte Carlo. It's really a combination of Monte Carlo and hypertemperature expansion calculations, which are shown in this rectangle. And they can be compared with the exponent extracted from this helium-4 data shown in this horizontal band. This is the sort of 1 sigma and 3 sigma error bars that they reported. And you can see that there's a discrepancy between the Monte Carlo results and the helium-4 exponents that came out of their experimental analysis. And so it's sort of a nice target for the bootstrap to try to resolve that discrepancy. But you can see that, at least in the study that I'm showing here, which was done, we did about 5 years ago, we weren't able to resolve this discrepancy yet. So, you can sort of ask, what does it take for the bootstrap to shrink this island more? Should we just be pushing to higher derivative order? That doesn't, that's computationally intensive. It doesn't help too much. You can sort of see that these islands aren't shrinking that much at higher derivative orders. But the other direction is to go to a larger system of 4-point functions and include more operators as external operators in the crossing equations. And so sort of using all these new software tools that I described at the beginning, we were able to do that and increase this to a system of 4-point functions involving the leading ON vector phi I, the leading singlet S, and the leading 2-index tensor. Let's call it TIJ. Or if you think of this as in sort of U1 language, it's the leading charge 0, charge 1, and charge 2 operators. So by going to this larger system, we were able to shrink the island by another, at least another order of magnitude. And so you can see this small black region is now the best bootstrap determination coming from studying a system of 22 crossing relations, and that can be compared with the most recent Monte Carlo simulations. Here's a zoom in. So you can see that there's actually sort of spectacular agreement between the best bootstrap island and the latest Monte Carlo computations done by Heisenberg. So they sort of give you some complementary information. But these give you values for the scaling dimensions or critical exponents that are very, very different from the value reported in the analysis of the helium-4 data. So now we can sort of definitively say that something went wrong in this analysis of the helium-4 data. Probably they underestimated their error bars in a fairly significant way, but we haven't completely understood what the origin of that discrepancy is. Okay, so here's another plot of the O2 allowed region that we obtained from this system of 3 correlators in delta S, delta phi, and delta T, just to show you that the bootstrap techniques can, for example, determine the scaling dimension of the leading charge 2 or 2-index tensor operator sort of much better, much more precisely than other methods, which are shown in this rectangle. Okay, so to actually do this computation, basically, we have to search over the space of 3 scaling dimensions, and we have to search over the space of the 3 ratios of OPE coefficients involving these external operators in order to get the best allowed region, and really input that these operators are all isolated and don't have some degeneracies associated with them. And so we really have to search through a 6-dimensional parameter space. So that's kind of a challenging thing to do. So we've spent some effort to develop, techniques to do that efficiently. And so, yeah, just to give you some sense, in order to really search through the 6-dimensional parameter space, we use a few ingredients. We sort of use this latest version of SDPB, which is more parallelizable. So we run this on a computing cluster. We use a technique called hot starting, where you can sort of use the solution for the functional obtained at one point in the 6-dimensional parameter space as the starting point for searching for a functional at another point. And that means you get to run this algorithm for fewer iterations. Then we have to search through the 6-dimensional parameter space. To search through the space of scaling dimensions, we're sort of using something that we're calling a Delaunay triangulation search. I'll describe that in the next slide. And then to search through the space of lambdas, we're using some tricks that we worked out, where each time you do a computation and compute a functional, you can actually use that functional to rule out a whole region of parameter space, rather than just the point that you tested. And so basically you can do one computation, rule out a big region, do another computation, rule out another big region, and you can use this to sort of cut down the allowed parameter space until you eventually find some point that's allowed. So we call this a cutting surface algorithm. This Delaunay triangulation search sort of looks like this. You basically take all of the points you have some set of points are allowed, some set of points are disallowed. You compute a triangulation of those points, and so there's some set of triangles involving connecting allowed points to disallowed points. Then the idea is basically you just pick the biggest one, using some sense of biggest one, and choose the center of that biggest triangle in order to decide which point you should compute next. And this sort of is an efficient way to find the boundary of the allowed region in a reasonable number of iterations. And then, as I said, with this cutting surface algorithm, we have this challenge that we need to find some allowed points in the 6-dimensional parameter space involving 3 ratios of OPE coefficients. And in practice, each time we do a computation, you get a functional. You can use that functional to rule out a whole sort of almost a half plane of parameter space defined by a quadratic inequality. And so you can basically use that to sort of whittle down the allowed parameter space until you get some small region, and then you test a point in the middle of that region and finally find something that's allowed. Okay, so that should at least give you a sense of what we're doing to actually map out this parameter space. Now we sort of use these same techniques. Yeah.
Just a question. So this, maybe I misunderstood, but this allowed region, would it always be convex?
In practice, it seems to be convex, but there's no argument that it has to be. I mean,
your methods rely on that convexity or not?
These methods, they don't require convexity. You can apply them to map out non-convex spaces, but they work better when it's convex. If you have some funny non-convex region, then it's sort of, it can be easier to miss small, if there's some small spike of the region that's coming out, then it, you can potentially miss that, or these search algorithms won't necessarily hone in on that funny non-convex part of the region unless you work harder to set it up so that it will find it. So but the search algorithms themselves don't assume convexity, but it's quite helpful.
But why the convex region only comes out? That's not understood, you're saying. I mean, why the allowed region turns out to be convex is not well understood, or is it?
Yeah, I don't think it's understood why that had to be.
Okay. Thank you.
And it's also, if you throw other assumptions into the Bootstrap problem, so like make some assumptions about the higher dimensional operators or other OPE coefficients, you can easily get into the situation where the allowed region is non-convex. So it's just sort of an accident that these sort of simple set of assumptions that we're using here carve out a convex region.
Thank you.
Hi, David.
Hi.
Just a general question, since you are talking about the comparison to experiment and Monte Carlo. So the 3-point functions, are there Monte Carlo simulations of those, and experiments? I believe no one has looked at anything like that, but do you think that's something foreseeable future one can aim for? Or have you talked to people who do these sort of experiments?
Let me think. I mean, in terms of Monte Carlo, I think there's a small handful of Monte Carlo studies which they're not very precise, but sort of coarse determinations of OPE coefficients. So that can be doable in some situations, but I think it's not super easy. Experimentally, I'm not sure. I don't
even
know.
something like the central charge. I mean, the phi, the stress tensor.
Well, so I mean, in some systems, people can experimentally measure quantities like conductivities. For example, you can measure. So for example, one case I know about is that it's possible to basically simulate the O2 model in a system of cold atoms trapped in an optical lattice. And by sort of applying a laser to it and varying the frequency of that laser, they could basically get a measurement of the optical conductivity, which measures the current 2-point function as a function of frequency. And at large frequency, that turns into the current central charge of the CFT. So that's at least one example where you can make some contact between central charges in some experimental system.
Yeah, I mean, you have all these numbers to high accuracy now. It would be wonderful to compare them with simulations or experiments. I would imagine.
That's right. Yeah.
One should probably canvas for it actively in the relevant communities, I suppose.
Right.
Yeah. Okay.
Yeah.
Thanks.
Yeah. I know. I mean, there's definitely a subset of the lattice community who's thinking actively about how to better determine the CFT data. So yeah, but that's definitely. I mean, also these theories seem to work well for the Bootstrap, but there are other interesting CFTs where the Bootstrap has a lot more trouble, and then it's very important to get lattice data to help us out. Okay, so we've also applied these methods to the 3-dimensional O3 model. Basically the same setup. We looked at the system of 4-point functions involving the leading O3 vector, O3 singlet, and O3 symmetric tensor, and use this. We again have a 6-dimensional parameter space to search through, use this cutting surface algorithm and so on to compute a sort of 3-dimensional island in the space of allowed scaling dimensions. And that, again, seems to have, basically a similar size as the scaling dimensions which have been computed using Monte Carlo simulations. most recent ones are again by Heisenberg. And there's again sort of very nice agreement. So we sort of honed in on one interesting question in the O3 model, which is the question of, if you look at the leading 4-index tensor, which you'd build out of fields like phi I, phi j, phi k, phi l, and symmetrize and subtract traces, you can ask if this is a relevant operator or an irrelevant operator in the O3 model. So there have been sort of a variety of studies in the past looking at this operator, and they all come up with numbers which are very, very close to 3. So it seems to be an almost marginal operator. You know, sort of more of the recent studies have pointed on the side of it being relevant, but there have been a few studies pointing to it being slightly irrelevant. So it's sort of a natural question for the Bootstrap to tackle. Can we determine whether this is relevant or irrelevant in the O3 model? And that's also sort of an experimentally very important question, because if you have a system like a magnet, which where the O3 symmetry is sort of broken at the microscopic level, for example, it could be broken to a cubic subgroup of the O3 symmetry. So if you have a system which is on a cubic lattice, then the interactions of the spins will prefer the directions along the cubic lattice, and will break O3 down to a discrete cubic subgroup. So if you have only a discrete cubic subgroup, then you're allowed to add this operator to the Lagrangian, and if it's relevant, then it'll cause your theory to flow to a fixed point, which is not the O3 model, but the fixed point of the cubic with a cubic symmetry. So we basically designed this new tip-top search that I mentioned at the beginning to tackle this problem. So in particular, try to find the maximum value of this scaling dimension of this 4-index tensor across this O3 island that we computed. And we were able to compute basically rigorous upper bound on the scaling dimension, which was 2.99. So we are now convinced that this operator is a relevant operator. So this is more or less a numerical bootstrap proof that, you know, what you would call critical Heisenberg magnets are unstable to cubic anisotropy. Okay, so that's sort of an interesting result to come out of our analysis. Here's a picture of what the tip-top search looks like. Basically the idea is that you sort of, we want to make different assumptions about the gap in this 4-index tensor sector. And at each value of the gap, we map out some approximate island in the scaling dimension space. Then we find an approximate island, then start increasing the gap, and then compute a new island, then increase the gap, compute a new island, and we do that until we basically find that we can't increase the gap anymore and still find any island left. So that's roughly how we compute the maximum value of this scaling dimension. Let me mention some other data we can get from these Bootstrap analyses. So there was a question earlier about higher dimensional operators. So here we computed islands for sort of the leading CFT data involving scalar operators, but of course there are lots of other operators in the spectrum. And we have one method to try to get at these operators, which is to extract something that we call the extremal spectrum. So the idea is that if you go to some boundary in the allowed region, it can be any boundary. It can be a boundary in scaling dimension space. It could be a boundary obtained by maximizing or minimizing some OPE coefficient. Then right on the boundary, if you look at what the functional applied to the conformal blocks looks like, you see that it has a discrete set of zeros. So it's basically right on the verge of going negative at some scaling dimensions, which would sort of get you into the region where when the functional is positive over this whole region, then that's when it can rule out those assumptions about the spectrum. So right along the boundary, it's on the verge of transitioning from being all positive to dipping negative somewhere. And the locations of those zeros sort of pick out a solution to the crossing equations that you can reconstruct, or at least a solution, an approximate solution to the crossing equations that you used in your numerics. So you can basically pick out the locations of these zeros, then you can solve for the OPE coefficients of these operators and get a spectrum. And by sort of moving around in this island and extremizing various quantities, you can see how this extremal spectrum shifts around. And as long as your island is sort of small enough, you don't see the extremal spectrum moving around very much, and you can get what seems to be fairly robust determinations of higher dimensional operators as well. So this is a non-rigorous approach, but in practice it seems to do quite well, and you can also think about trying to upgrade these determinations to more rigorous ones using the similar convex optimization techniques. So you can sort of look at the locations of these zeros. This is just, you can make these kinds of scatter plots where you show for each value of the spin, what are all the operators that you see as zeros in the spectrum. In this plot, the size of these circles, shows you that we tested a bunch of different points in this island. We moved around on the island, and the size of the circle shows you in how many of those extremal spectra do you see an operator at that location. So sort of big circles correspond to robust operators, which are in all of the extremal solutions that we looked at, and small circles mean they're sort of not very robust, and probably you can ignore them. But at least at low, so this is showing spin versus twist. Twist is dimension minus spin. At least at low twist, you see some fairly robust trajectories of operators as a function of spin. And this is actually very interesting data that you can then compare with analytical bootstrap techniques, which also predict trajectories of operators as a function of spin. So in particular, there are a couple different analytical approaches that have been developed. One approach is called the light cone bootstrap, where you basically study crossing symmetry in a light cone limit, where you take one cross ratio to 0, making two of the operators light-like separated from each other. And by analyzing crossing in the light cone limit, you can see that the spectrum on one side of the crossing equation, you have like the identity operator and the other leading twist operators. And then to match that on the other side of the crossing relation, you need a trajectory of operators of increasing spin. And you can basically establish that these trajectories need to have twist asymptoting to twice the scaling dimension of the external operator, 2 delta sigma. And then you can analytically calculate corrections in the 1 over spin expansion, which depend on the other sort of leading twist data in the spectrum. And then more recently, this light cone bootstrap was sort of upgraded using an approach called the Lorenzian inversion formula, where you can basically relate these trajectories of double twist operators to a certain integral of a double discontinuity of the 4-point function. This was introduced by Simone Caron-Huot a few years ago. And this Lorenzian inversion formula, you can basically use it as another approach to studying these trajectories. And if you, for example, approximate the double discontinuity of the 4-point function using the first several leading twist contributions that you know from the numerical bootstrap, then you can basically evaluate these integrals explicitly in terms of a big sum of 4f3 hypergeometric functions. So this gives you sort of a, the result that you get out of this approach basically has the same asymptotics as the light cone bootstrap, but also can give you some information about what the trajectory is doing at low spin. Okay, so just to show you some plots comparing the analytical bootstrap approach applied to the O2 model, shown in these curves. So these three different curves are showing the charge zero sector, and the charge 2 sectors. Sorry, charge 2. Yeah, so the charge 0 and charge 2 sectors. If you look, for example, at the leading charge 2 sector, you can see that there's an operator down here at, sorry, let me say that again. If you look at the leading charge 0 sectors, you have some operators down here at twist exactly equal to 1. And so those correspond to the stress energy tensor and O2 current, whose scaling dimensions are fixed. And you can see that these data points shown in this plot are the data extracted from this extremal spectrum approach. And you can see that these analytical curves computed using the Lorenzian inversion formula method basically go right through most of these data points. In particular, it seems to work all the way down to spin 2 and even down to spin 1. So there seems to be excellent agreement between this extremal spectrum approach and the Lorenzian inversion formula approach. Even just by, here we just approximated this double discontinuity using the first few operators, which we know from the numerical bootstrap. Another thing that we saw is that, you can look at other trajectories of operators. So for example, we can look at the leading charge 1 operators. There, you can see that there's sort of interesting mixing which happens between the double twist operators. So you can construct a double twist operator between phi and s of charge 1, but also a different tower of double twist operators between phi and t, where you contract one of the indices of charge 1. This is an O2 vector. And these operators have some mixing with each other because their twists are relatively close. And we sort of understood in the context of the Lorenzian inversion formula how to diagonalize the mixing between these two towers of operators. And after doing that, you get sort of better agreement with the numerical data. So that's what this plot is showing. Without diagonalizing these mixing effects, you sort of, the curve is a little bit off at low spin, and after diagonalizing them, it looks quite a bit better. It's even more dramatic if you look at the charge 1 odd spin operators. Okay. Finally, let me mention that you can basically extrapolate these curves down to low spin and see what happens. And so if you sort of go in and see, how low in spin do you get before the curve turns around and starts moving up again, this could be visualized using something called a Chu-Frouchy plot, where you plot the scaling dimension minus space-time dimension over 2 on one axis and spin on the other axis. And you can look at where that curve intercepts delta equals 3/2. This intercept is actually a very interesting number because it's something called the Regge intercept. the value of the intercept is interesting because it basically controls the behavior of the correlator in a particular Lorenzian limit called the Regge limit, which is sort of easy to think about in a holographic dual description, where the Regge limit corresponds to sort of considering 2-to-2 scattering at high energies, but a fixed impact parameter. And that has a precise analog in terms of the CFT correlation function by analytically continuing one of the cross ratios, say around 1 through a branch cut, which starts at 1, and then sending both cross ratios to 0 at a fixed ratio. Okay, so one of the other outcomes of this kind of study is that we can make the first determinations of the Regge intercepts of in this case, the O2 model, and there's a similar study of the Ising model done by Karanhyo, Gobe, and Zare, shown on the right. Okay, so let me just take a few more minutes. I'll try to, I know I'm running low on time, so I won't go too long. But just to give...
Sure, yeah. You can take a few more minutes, no problem.
Okay, thank you. So yeah, let me just show you sort of one of the other sort of frontiers of the Bootstrap, which is sort of extending the Bootstrap techniques to correlation functions involving spinning operators, external spinning operators. So, okay, so as I mentioned at the beginning, we recently developed this new software called Blocks 3D, which gives you sort of an efficient method for computing arbitrary conformal blocks involving spinning operators in 3 dimensions. This makes use of a kind of recursion relation that the blocks satisfy, where they can be expanded in a sum over poles in the exchanged scaling dimension. The locations of the poles have a nice sort of group theoretic interpretation in terms of sort of non-unitary scaling dimensions where the exchanged operator has some descendant, which becomes a null state. And then the residue of that pole becomes proportional to the conformal block of that null state and all of its descendants. And so this actually gives you a sort of recursive method to evaluate the conformal blocks, very similar to the Zemlya-Lodzhikov recursion relations, which could be used in 2 dimensions to evaluate Virasoro conformal blocks. So we made sort of an efficient C++ implementation of this recursion relation, and it seems to be fairly practical for computing conformal blocks, at least involving low spin operators like fermions, currents, and stress tensors in a reasonable amount of time. Okay, so the other thing we've been doing is sort of applying this new software to try to tackle problems that were not so easy before. One interesting application is to just looking at the Bootstrap involving fermions. So we did some study a few years ago involving fermion 4-point functions in 3 dimensions. But we couldn't push it very far using the technology at the time. And so we recently revisited these bounds from 4 fermion correlation functions. So something very curious happens when you look at a 4-point function of fermions and bound the leading parity odd scalar operator sigma appearing in the fermion-fermion OPE. You basically see a bound which starts at 1, 2. So this is like a free fermion theory. And then it goes up, goes up, goes up. And then at some point it has this very sharp jump. Jumps from a little below 3 up to 7. And then it keeps going to the right. So this is a very curious thing. You ask, what is the interpretation of this really sharp jump in the Bootstrap bounds? There was actually a proposal for what could explain this using something called the fake primary effect, where the idea was that our bootstrap problem allows for spin 1 parity odd operators at the unitarity bound to show up in the OPE. But actually the conformal blocks, if you look at the conformal blocks of a spin 1 parity odd operator approaching the unitarity bound, they sort of become degenerate with the conformal blocks of a dimension 3 scalar for some group theoretic reasons that were understood in this paper by Karateev, Kravchuk, Saroni, and Vicky. So the idea was that if you sort of remove these spin 1 operators at the unitarity bound from the bootstrap problem and pose some gap in that sector, then maybe this jump will go away. And so we just explored what happens when we increase the gap in that sector. And the expectation was that it would sort of go away right immediately. The jump would go away immediately when you remove the primary effect. Here we saw that we have to make the gap fairly sizable before the bound comes down again. So we had to bring it up to something like 2.3 to 2.35. So this is still kind of a mystery. It didn't quite seem to be explained by removing the fake primary effect to our satisfaction. So there's still some possibility that, maybe there's some interesting CFT living up in this jump, the top of this jump or this spike. And if there were, then it would be sort of a very interesting conformal field theory, because it would be a conformal field theory where there are no relevant scalar operators in the spectrum. By the way, this plot is showing the leading parity odd scalar, but you can also study the leading parity even scalar and also see that it actually has a kink in the bound at a similar location, and that kink is also at an irrelevant location. So anyway, so we have this sort of conjecture that maybe there's a theory living up here, but we'd like to understand it better. Okay, let me just show you one other application of these numerical bootstrap techniques to theories with fermions. So there's another class of interesting CFTs involving fermions called the Grosnovo-Yukawa models. So in a Lagrangian description, you can think of them as being like the theory that you get when you have n fermions psi I, and you couple them to a scalar sigma, you through a Yukawa coupling, and then potentially also give that scalar some quartic coupling. So this gives you the Lagrangian of the Grosnovo-Yukawa model, which at least at large n, you can establish has a fixed point. There are also variations of these kinds of models involving more than one scalar as well, which also have some interest. Yeah, if you sort of scour through the condensed matter literature, you can find various applications of these models, like in the case with 8. Here I'm counting the number of Majorana fermions. So in the case of 8 Majorana fermions, there are possible applications to critical points in D-wave superconductors or models of graphene. At n equals 4, there's a model called spinless fermions on the honeycomb lattice, which is studied in Monte Carlo studies, and other models of gapless semiconductors. So there are various applications of these theories. So they're sort of an interesting target for the bootstrap. This is just to show you that we know for the operators in these Grosnovo-Yukawa theories, we know what the operators do at large n. Here I'm just showing some of the leading large n predictions. In many cases, we know the next order correction as well, but it doesn't fit nicely on a slide. Let me just draw your attention to the fermion in the theory starts at 1 plus 1 over n corrections, and the leading parity odd scalar in the theory sigma starts at 1 minus 1 over n corrections. And then the other sort of low dimension operators, there's the leading parity even scalar, which starts at 2, and the leading parity odd 2-index tensor, which also starts at 2. So you can place bounds on these various sectors using the bootstrap techniques. Here's the bound in the leading parity odd 2-index tensor for different values of n. And actually these bounds sort of have an interesting structure to them. They start at the 1, 2, the free values, they go up, and then they have a kink in them. And at least at large n, the ON Gross-Niveau-Yukawa models seem to sit near these kinks. The situation at small n is a little bit murkier, but there may be still some kinks that you can identify up here at small n. So that seems promising. It seems like maybe the bootstrap knows something about these Gross-Niveau-Yukawa models. And you can also place bounds in the psi sigma plane, where sigma is the leading parity odd ON singlet operator. And if you assume that sigma is the only relevant operator in its channel, you get some interesting sort of lower bounds, which sort of have some funny wave structure to them. There are these like kinks in the tips of these waves, and those seem to sit fairly close to, say, previous predictions for the Gross-Niveau-Yukawa models in the epsilon expansion. So this seems to be sort of carving out some regions that are close to the Gross-Niveau-Yukawa models. So what I wanted to mainly show you is that actually we've now used all this new technology for the bootstrap to go to a system of correlators involving external fermions and external scalars. So this is a system of, I think, 38 crossing equations. So it's a fairly big bootstrap system. But using the system, we've been able to get a closed island, in this case around the n equals 2 Gross-Niveau-Yukawa model. So we basically could turn this tip into some island, which is right around this point. To get this island, we have to make various assumptions about gaps in the different channels. These gaps that we've chosen are sort of motivated by this large n spectrum that I showed you over here, and are hopefully chosen to be safe even at small n. But sort of using these mild gap assumptions, we can carve out a region. So this region is shown at fairly low derivative order. So right now we're sort of working on pushing it to higher derivative order, and also computing these islands for other values of n. But this seems like another class of 3D CFTs, which are going to be sort of naturally amenable to bootstrap techniques. Just to show you we're getting numbers shown below here for the scaling dimensions of psi, sigma, and epsilon, with errors currently in the third or second digits. These look pretty similar to numbers obtained using Borel resummations of the epsilon expansion done by this collaboration. The previous estimates for the scaling dimension of epsilon, which is related to the new critical exponent, have sort of been all over the place. You can see they got 1.5, we're getting 1.77. So this seems to be a place where the bootstrap is going to add something new to our knowledge of these theories. Okay, I'll just show you one last theory that I've been interested in, which is sort of the, if you like, it's the n equals 1 Gross-Niveau-Yukawa model. Or if another perspective is that it's the minimal supersymmetric extension of the Ising model. So this is a theory with one real scalar sigma, one Majorana fermion psi, and they can have a Yukawa coupling and a quartic interaction. And if those couplings are related to each other, then the theory has curly n equals 1 supersymmetry in 3 dimensions, which this can be captured by a theory with a cubic superpotential. So this theory also has some potential experimental interest. It's been proposed that it might be realizable as a theory living on the boundary of topological superconductors, which can support Majorana fermions propagating on the 2+1 dimensional boundary. As far as I know, this hasn't actually been realized in practice yet, but it's a proposal. So this is also an interesting target for the Bootstrap, because you can, sort of throw in all the constraints of supersymmetry into the Bootstrap system and, get those constrain the system even further. And so we've been able to compute fairly small islands for this supersymmetric extension of the Ising model, which basically look at correlation functions involving sigma and epsilon, impose all the constraints of curly n equals 1 supersymmetry, which relate, OPE coefficients of operators within a supersymmetry multiplet to each other. And then also we assumed that sigma and epsilon are the only relevant operators in their symmetry channels, and we can get a fairly small island for this theory, which seems to be compatible with previous estimates from the epsilon expansion. Okay, so that's basically all I wanted to show you. This is just one more plot showing sort of the map of the allowed space of scaling dimensions, which we computed using the Bootstrap for stress tensor 4-point functions a few years ago. Now we're trying to push this much further using all the new technology that we've developed, thinking about sort of correlation functions involving stress tensors and scalars, and stress tensors and fermions, and so on. But here, this plot is showing you, in a 3D CFT with a parity symmetry, the x-axis is the leading parity even scalar, the y-axis is the leading parity odd scalar, and you get some exclusion plot from the numerical Bootstrap, and you can identify, lots of known solutions in this space. So a free scalar theory actually lives up here, where the scaling dimension, there's a scaling dimension at 1 and 11, so it's actually very hard to build a parity odd scalar operator in a theory of a single free scalar. You have to use a lot of derivatives and an epsilon tensor and so on. Free fermion theory lives over here at 6,2. The large n limit of the ON models lives here at 2,7. The large n limit of the Gross-Navo-Yukawa models lives down here at 2,1. The Ising model, we think, lives at the top of this, somewhere at the top of this jump. And this minimal supersymmetric extension of the Ising model, or n equals 1 Gross-Navo-Yukawa model, lives down here. So you can sort of see that you can identify known theories as living in corners of the space. And so one task for the Bootstrap going forward is going to be basically to refine this map of the space of 3D CFTs, and sort of turn this kind of plot into a plot with lots of little islands all over the place. Okay, so that's basically all I wanted to tell you. There's lots of sort of interesting directions to go from here. I'm interested in these fermionic models. Another important target that I'm working on, but we don't have completely have satisfactory results yet, are for studying gauge theories using the Bootstrap. So we're looking at 3D QED and eventually 4D QCD in their conformal windows. There's a whole zoo of super conformal field theories that are interesting to study using the Bootstrap. And sort of all these future directions involve pushing to larger systems of mixed correlators, probably involving spinning operators, which in turn involves improving our algorithms and software tools. Another interesting direction is to explore the Bootstrap of higher point functions, which might be a more efficient way to sort of get additional constraints rather than looking at arbitrary 4-point functions involving spinning operators. And then there's also this analytical direction where we have the Lorenzian inversion formula. There's a related approach called developing conformal dispersion relations. And ultimately, I hope we can sort of incorporate all the analytical insights we gain from these approaches, like the fact that we know the large spin spectrum very, very precisely, into improving the numerical algorithms and sort of coming up with a very fast, efficient way to bootstrap this whole space of 3D CFTs. So, all right, so I'm going to stop there. So thanks a lot for listening.
Thanks a lot, David, for the great talk. So is there any question for David? Yes, so something I was wondering is, you mentioned this Ray-J intercepts, and also the connection with holography.
Yeah.
But what are really the prospects of applying these techniques to like holographic theories holographic CFTs? Can you do it or? Yeah,
I mean, sure. So you can apply these. I mean, certainly, the analytical bootstrap approach you could definitely apply to large N theories. Develop the analytical bootstrap in the one large N expansion. Apply it to holographic theories. There's sort of interesting things you could do, like studying the bootstrap and the Reggie limit in holographic theories. And so there's lots you can do there. In terms of the numerical bootstrap, you can also make contact with holographic theories. Sorry, let me just go back to. So let me just go back to this plot. So like holographic theories, contain the graviton, which is dual to the stress tensor, and then they contain multi-graviton states, which correspond to operators built out of multiple stress tensors. So that's actually what this point is right here, which I labeled as mean field. So this dimension 6 operator is an operator that you build out of 2 stress tensors, which would be a 2 graviton state. And then there's similarly a parity odd operator you can build out of 2 gravitons. So holographic theories sort of want to live up in this corner. Now, you can sort of try to play games where, like in a holographic theory, you expect, higher spin operators or higher spin single trace operators to decouple. So you can try to like impose a gap in the leading spin 4 spectrum and see how big can you make that gap, and does that constrain theories. One issue you run into is that there are also spin 4 operators built out of 2 stress tensors, like T mu nu, T rho sigma, so multi-trace type operators. And from the numerical bootstrap perspective, it's kind of tricky to disentangle those multi-trace operators from the single trace operators. So what you'd really like to do is, impose a big gap in the spectrum of single trace operators, but you sort of, in the numerical bootstrap, you run into all the multi-traces and have to come up with a way to deal with them. So that's sort of one of the challenges to applying the numerical bootstrap techniques to holographic theories.
I see. Okay.
But yeah, but that's definitely a direction that you can go down. And then, as I said, there are also a variety of analytical bootstrap things you can do related to holographic theories.
Okay. Thanks.
Yeah.
I have a question. Why are interesting CFTs at the kinks?
Yeah. So let me just go back to, that's a good, obviously that's like one of the first questions, you should ask. So it's, I would say it's not fully understood yet. One way you could think about this is that there's some, family of solutions to crossing which live along this upper line. And then if you keep going past this kink, then something becomes non-unitary. So some, say some operator has a coefficient which is going down to 0 as you approach this kink, and then tries to go below 0 if you continue that family of solutions. And similarly with this curve. So, one way you can think about these kinks is that they correspond to positions where some operator has a coefficient which is going to 0 as you approach it. And so some operator is decoupling from the spectrum. And that actually seems to be the case sort of in practice where, if you look at the spectrum, the extremal spectrum corresponding to this boundary away from the kink, it has more operators in it than the spectrum right at the kink, where some operators decouple. That decoupling of operators seems to be related to the sort of equations of motion of these theories. So like in the Wilson-Fisher description of the Ising model, it's a scalar with a quartic interaction. You have some equation of motion like del squared phi equals phi cubed. And that's telling you that the phi cubed operator is really a descendant of phi. It's a derivative of phi. And so you don't expect it to be in the spectrum of primary operators in the CFT. So as you approach the Ising model solution, that phi cubed operator decouples. Whereas if you look at solutions sort of nearby, they do have this phi cube operator in the spectrum. So that's sort of our best understanding right now. The kinks are sort of related to, they emerge when operators decouple from the spectrum, so you'd violate unitarity if you kept going in that family. And that decoupling of operators seems to be related to the fact that physical theories have some underlying equations of motion which decouple the operators.
Okay, I see. Right, but when you looked at the mixed correlators, you found like this island, and then you had like what do you call it, the mainland or something?
Yeah, this
so okay, so you're saying that at this island, there you see, I mean, maybe some effects from the equations of motion or something, that phi cubed is a descendant and decouples.
Yeah.
But then at this the mainland.
Yeah.
So are these some other kind of interacting CFTs or?
Yeah, that's a good question. So you can ask, are there other interacting CFTs in here? So actually one theory which is almost in here is this supersymmetric extension of the Ising model, so the scaling dimension in that theory was like 0.58 and 1.58 on this plot. So it's like sitting right up here. I say almost because it doesn't. It has another operator at dimension like 2.9. So it doesn't quite satisfy this assumption of sigma and epsilon are the only relevant operators, but it almost does. So that solution is sort of, approximate solution is sort of in this region. If you go further to the right, then you can also find like generalized free theory solutions where the correlation functions factorize, like a 4-point function factorizes into products of 2-point functions. So if you go far enough to the right, you can find those kinds of solutions compatible with the assumptions that we made. I don't know of any. This is a very low derivative order plot, so at higher derivative order this mainland pushes further to the right. But I don't know of any other theories that would be sort of obviously sitting in this land.
Yes.
Right around where it's shown.
Thanks.
Yeah.
But okay, sorry. So if I will kind of like reverse this thing you said with the equations of motion and so on.
Yeah.
So for example, if you take this gross nouveau, okay, I can't pronounce it, the G and Y model, and then you look at the equations of motion. Can you use this as some kind of input to find the kink?
Yeah. Yes. So that's something we're basically trying to do. So let me go. Yeah. So here's the Lagrangian. So for example, the equation of motion for the fermion tells you that psi sigma, some linear combination of psi sigma and sigma cubed are a descendant, and then the other linear combination is not. And so that's if I go look at this table. So that sort of psi sigma operator is not present in this table. That would have been like, that operator would have been a low dimension parity odd ON vector. So this chi, like this chi sector. But because of the equation of motion at large n, the leading operator in that parity odd ON vector sector starts at 4 rather than 2. So, and then to compute this island, we're actually imposing a fairly big gap in that parity odd ON vector sector. Here we impose 3.5. And so that imposing that gap is sort of effectively imposing that equation of motion constraint, that the equation of motion tells you that they're, a priori you'd expect a low dimension operator in that sector, but here we're imposing a big gap to forbid it from existing, and that actually helps you very much to carve out this island.
I see. Thanks.
Yeah.
Any other question for David? Yeah, perhaps something a bit naive, that a bit a naive question. When you say that the bounds are rigorous, like, is it like rigorous, like mathematically rigorous, or could you miss some little, island or I don't know what in when you do these exclusion plots?
Yeah. So okay, people have different standards of rigor. So a mathematician wouldn't call this rigorous, but the logic that we're using to exclude points in this parameter space is, if you find a functional that has the properties that we're looking for, then that point would be rigorously excluded. So it's sort of numerically, we test these points and we find a functional, then we would say it's, at least numerically, it's rigorously excluded. Then there's the question of whether we've sort of mapped out these allowed regions fully. So you can see, like in this plot, there's really just, there's a finite number of points that in practice we can test. So yeah, of course, it's sort of possible that there's some funny spike of the allowed region that comes out that we missed. But it seems pretty unlikely. So, if you make an assumption that the allowed region is convex, and then we have some, under that assumption, we have some sort of shell of disallowed points, and we have some shell of allowed points. And if we assume convexity, then, modulo numerical precision type issues, we can get a rigorous bound.
Okay, yeah, okay.
Yeah.
Thanks.
Yeah.
Any more questions? Okay, if not, I guess we can all thank David again for the great talk.
All right, thanks a lot. You should all enjoy your dinner.
Thanks.
Thanks.